Great. And I think we're ready whenever you are, Gary.
Okay. Okay, well, as I said, I'd like to view this as a Blackboard talk and keep it informal, so please feel free to interrupt with questions at any time. I'd like to talk to you about a recent paper I wrote with my students, Sergio Hernandez Cuenca, Gabriel Trevino, and Dian Wang. It was put on the archive about a month ago, and it concerns boundary causality violating metrics in holography. So let me start with a puzzle. Of course, a fundamental property of any quantum field theory is causality. So we expect for any quantum field theory that if you take the commutator of two operators at space-like separated points, it will vanish for all sort of x and y space-like separated. But in holography, this has to be reproduced by a quantum gravity calculation in the bulk. We, of course, don't have a non-perturbative formulation of quantum gravity independent of holography, but a common approach, which we're going to adopt, is to consider a path integral over all metrics, in this case, all asymptotically anti-de Sitter metrics. So we want to consider, as the bulk quantum gravity theory, expressions like the following. We're going to consider path integrals over metrics, matter fields on the space-time, e to the I, the action, and then whatever fields we want to compute correlators of, where P and Q are points in the bulk. Since we're interested in questions of causality, G will of course be Lorentzian, and as I said, asymptotically anti-de Sitter. Well, some people have said that maybe the metric is not the fundamental degree of freedom in quantum gravity, and it'll be something else, but the metric will only arise in some low energy approximation. The argument I'm going to give will plausibly apply in that case also, because we're only going to be interested in spacetimes where the curvature is everywhere well below the Planck scale or the string scale. Okay, now often people work in a semi-classical approximation, and in a semi-classical approximation, we start with a solution of some supergravity equations, and the supergravity theories of interest all satisfy the null energy condition. And so in a semi-classical approximation, we have the so-called null energy condition satisfied. It's a statement that the stress tensor of the matter fields contracted with the null vector twice is non-negative. And in that case, there's a famous result of Gao and Wald, which says that the fastest way to get from one point on the boundary to another point on the boundary is through a curve, a null curve that stays on the boundary. Any trajectory which goes in the bulk will arrive later. So that's this Gao and Wald theorem from 2000. I'll just say the fastest curves stay on the boundary. Even when you have quantum matter fields and you can violate the null energy condition, there's an average null energy condition. People sometimes write the expectation value of the stress tensor contracted with the null vector twice, integrated over a null curve, integrated over a null geodesic. So this average null energy condition is believed to be satisfied, and that is enough to ensure that the same thing is true, that you can't violate boundary causality. But
Barry,
yes,
are you going to care about the distinction between the average null energy condition and the achronal average null energy condition at all?
no, I'm not. I guess it's the achronal average null energy condition which is needed. I mean,
Well, that's the one believed to be true.
That's the one which is believed to be true. Okay, and that's the one which is sufficient for ensuring boundary causality, right?
I believe so.
I believe so also. Let me just put achronal average null energy condition. Yes, yes, I think that's all that you need. That's the one that's supposed to be true, and that's what ensures that semi-classically there's no problem. Okay, but I want to go beyond the semi-classical approximation. I want to consider full quantum gravity, and in the full theory, so in holography, you should think of this as finite n, right, where n is the SUN of the dual gauge theory. Then you're integrating over all metrics, and there are certainly metrics which do violate boundary causality. And what I mean by that is that you can have 2 points on the boundary which are space-like separated according to the boundary metric. So we'll have a point X and a point Y, and from the boundary standpoint, they're just space-like separated points. But according to the metric in the bulk, these points are now time-like related. So X and Y would look like that according to the bulk metric. Okay, so these metrics certainly exist. And if you consider bulk points, say P and Q, in an asymptotic region that approach X and Y, one expects, so if P and Q sort of go to X and Y on the boundary, you expect a bulk calculation of a commutator of a bulk field at P and a bulk field at Q. You expect that commutator to be non-zero because they're time-like separated points in the bulk. And you expect this commutator to be non-zero even in the limit when P and Q go to the boundary, because according to the bulk metric, they are still time-like related in the bulk. Okay, so this would seem to produce a potential violation of boundary causality unless the integral over all metrics of this commutator vanish. So you would require something like that the integral over all metrics of e to the I times the gravitational action of the commutator of these fields. You require that to vanish exactly. Even a small quantum correction would be a problem, right? We don't want any non-zero value for this commutator. Yes, Raphael?
Just a quick question. I've seen enough of your paper that I'm already sure that your resolution is much better than this, but is there an argument why it's obviously crazy to just exclude those metrics from the path integral?
We certainly thought about that, but it does seem crazy because there's nothing wrong with them from the bulk standpoint. As a bulk metric, these metrics are perfectly fine. I'll give you examples in a second. They don't have closed time-like curves. They don't have any causality problem. They are perfectly good Lorentz metrics. The curvature can be small. They can be actually very close to ADS. Small deformations of ADS. I mean, all you have to do is imagine opening the light cones in ADS a bit, and you're in this situation where you can find points on the boundary which are space-like separated and then time-like separated in the bulk.
I guess it's completely non-local, right? I mean, there's never anything locally wrong with such a metric.
There's never anything locally wrong with the metric, right? Yeah. And even in finite regions, in the bulk, they look perfectly fine. It's only when you go out to the boundary and compare with the boundary metric that you get this apparent causality problem.
Yeah, that makes sense.
Okay, so this is what we require, but the problem is that this seems very unlikely to be true in quantum gravity. It's unlikely for several reasons, and let me just list a few of them. First of all, there exists lots of causality violating metrics. Boundary causality. I'm never ever going to violate causality in the bulk. As I said, no closed time-like curves. They're all nice spacetimes, but lots of causality, boundary causality violating metrics. And in fact, given one, you can clearly perturb it in any way you want. And if you have 2 points which are time-like separated in the bulk, according to one metric, any perturbation of that metric will keep those points time-like separated. And therefore, the set of these boundary causality violating metrics is open. So there's an open set of such metrics in the space of metrics. Second of all, many of these metrics have exactly the same action as ADS. There's no barrier to accessing these metrics that violate boundary causality in terms of the action. And it's easy to see that because if you just think about the space of all metrics, so this is all asymptotically ADS metrics, the action is just a function on this space. So this, the constant action surfaces are codimension 1. So this is constant action, and ADS is some point, but there are clearly lots and lots of metrics with the same action as ADS, and some of them will have this property that it violates boundary causality. So it's a codimension 1 surface of metrics that have the same action. Finally, it's not just one integral that has to vanish exactly. You can choose any operator to consider the commutator of in the boundary, and you can take that commutator and multiply it by any other operator you want. So there's basically an infinite number of integrands that have to all integrate to 0 exactly. Okay, and that seems very unlikely. So that's the puzzle. Okay, we have something which must be true in the field theory, seems very unlikely to be true from the bulk standpoint, And that's the puzzle I want to resolve today. So let me just
Can I
stop.
just ask about the third point? Yeah, sorry.
Yeah, go ahead. I'm asking for questions. Yeah.
Yeah, about the third point, just to make sure I understood, you're just talking about turning on sources at the boundary, where you send in stuff, for example, and then you'll always have to integrate over that, over a
No,
class of metric that includes these sources, or?
no, not necessarily. I'm just thinking about more complicated operators. You could take, any correlation function in the field theory, which would be, some, involving lots of fields in the bulk, and you multiply it by this commutator, and that has to vanish. According to the boundary, any sort of product of operators, multiplied by the commutator is strictly 0, whereas in the from the bulk standpoint, it would not look 0, and it would have to vanish only after integrating over all metrics.
Is that this? I'm still a little confused. Is that different from saying that it has to vanish for every state of the boundary theory?
Yes. Well, let's see. It's related. Let's see. If you start adding lots of operators, yeah, that's probably closely related to saying that this commutator vanishes as an operator statement, not just inside expectation. Yeah.
Your requirement is weaker in a sense that you require all these commutator to vanish on the states which has a semi-classical interpretation. But the things are correct as an operator equation is equivalent with it vanishes for all states, right? But it's simply like semi-classical superposition of semi-classical geometry is not spanning the entire state.
Right. I'm not considering states in the field theory, which would be superposition of semi-classical metrics, right?
Oh, yeah. Yes. Or even something you don't have that kind of interpretation, right? It's just
right.
Garbage, typical states, and so on.
Okay. Well, let me next just give you some simple examples of metrics that have this problem. And so and they can be quite simple. So if you just start with static, spherically symmetric, 4-dimensional metrics, they typically, well, we can consider metrics which are actually defined by just one function, f of r, some dr squared over f of r plus r squared d omega. So this class of metrics defined by f of r will be asymptotically ADS. Yes, if f at large r is equal to r squared, I'll set the ADS radius equal to 1 plus lower order terms. And pure ADS is, of course, just the case where f is equal to r squared plus 1. Okay, but now if you look at the radial null geodesics that just go through the center of ADS from one boundary point to the antipodal point on the boundary, it will take a time, according to this metric. Well, the radial curves clearly have a dt equal to dr over f. So this will equal a time, which is just twice the time it takes to get from the origin to the boundary. And so it's twice the integral from 0 to infinity of dr over f. Whoops. Okay. So in ADS, that's of course just pi. And so if you just take any metric in which this integral is less than pi, you clearly are going to have a metric which violates boundary causality. Curves through the bulk will reach the boundary faster than the light curve, which stays on the boundary. You'll connect space-like separated points with time-like curves going through the boundary. That's clearly easy to do. Any function f, which is bigger than f naught, everywhere asymptotically approaching r squared will do that. Lots of other metrics will do that as well. Furthermore, okay, so these metrics, well, we'll have to, on the initial and final slice, match up to a metric which takes this form. But if you want to fix some other metric on the initial and final slice of your path integral, you can clearly change this metric near the initial and final slice to reach any boundary condition you want and not affect the causality violating region in the middle. You only need a time of order pi in the middle to see this causality problem, and then you can have it modified elsewhere. Furthermore, if you want these metrics to have the same action as ADS, well, that's easy to do. In fact, as I said, the action is just one number. You can keep this causality violating region, change the metric some other place in some way that will make this one number, the action, equal to the action for pure ADS. So can vary. So we can easily modify this metric to match initial and final boundary conditions. And if we want to have the same action as ADS itself. Okay, so let me
Gavin?
next, yes, question?
Yeah, maybe I just want to make sure I'm not missing something. Why would we want it to have the same action as ADS? I mean, we never say that we integrate only over configurations with a particular value of the action, right?
Right, you're absolutely right, but it, okay, so in thinking about how this might be zero, right? What we would need is that this integral always is exactly zero. So you think about, well, how can it be zero? The only way it can be zero is if you get all these cancellations coming from the different phase of e to the is.
Mm-hmm.
All I'm saying is that in the infinite dimensional space of metrics, all but one dimension is going to give you a metric which has the same action, and therefore you get no cancellation from that. So the cancellation comes, if it comes at all, has to come from a one-dimensional integral, only integrating over directions normal to these surfaces of constant action. So there are metrics which have action different from ADS, but you can imagine doing the integral over metrics by first integrating over metrics of constant s, in which case you get no cancellation, and then the cancellation has to all come from a one-dimensional integral.
And that's how you actually organize the argument. I mean, mathematically, this is clearly correct, but what you're probably saying that this is also how it's useful to organize the argument that way.
Well, when we were working on this, when we were working on this project, we thought for a long time that this integral had to vanish, and we tried to find an argument why it had to vanish. And when we were trying to estimate this integral, that's what we did. We divided it up, so these integrals, so that over constant s, and we were left with this one-dimensional integral. And so it all had to come from a one-dimensional integral, basically, over this. I mean, that's all I'm saying. So it makes it seem even less plausible. If you're thinking about infinite dimensional integrals, you say, well, anything can happen. But when you realize it all can be reduced to a one-dimensional integral, then you get more worried. And that's why we came up with another argument.
Oh, I see.
So the answer is not going to be a proof that this integral always vanishes. That's not the answer. I'm going to give you a different answer.
You're telling me I should be more worried in light of the fact that it comes down to this one-dimensional.
We were more worried. Yes.
Okay.
Yes. Okay. So let me now just remind you of two different ways of relating bulk and boundary quantities in holography. And these are something I can call two dictionaries. That have been discussed in the literature. First, we have the original correspondence. So this is the, I'll call this A. It's the statement that the bulk partition function, which is, I'll explain the notation in a minute. Basically, it has to be equal to a boundary partition function. Z boundary here is just the usual partition function of, okay, so this is a partition function. Partition function of a CFT on some space. It's a manifold B and has some metric gamma. And phi 0 are sources for all the possible local operators and the CFT. And phi 0 denotes some generic, denotes sources. The local operators. Z on the left-hand side, we have a bulk partition function. This involves, well, it says it's the integral over metrics conformal, well, metrics with the same space B gamma as a conformal boundary. As the conformal boundary, and phi naught are the boundary conditions for all of these bulk fields. Sort of the boundary conditions for the bulk fields. Okay, so this is the original form of the correspondence. It's the one that's often studied. To be a little bit more explicit, this Z boundary can be thought of as just the sort of expectation value in the CFT of an operator, which is e to the I times the integral over the space-time on the boundary that the field theory lives on. And then a sum over all of these sources times operators. And therefore, if you want to get any correlation function, you can just differentiate with respect to these sources. And that's why this is called the differentiate dictionary by some people. I think Dan Harlow first suggested this, but differentiate. As a way of describing this correspondence between the bulk and the boundary. Okay, this is one way that people have discussed in holography, but there is another way. And that is just to start with a bulk correlation function and take the limit with a suitable rescaling. There's actually two ways to imagine doing this in full quantum gravity. So the second one is to take the limit of a bulk correlation function. So you would write down something like a correlation function, an endpoint function of some operator in the boundary is equal to or related to a limit. Well, let me first write it in this way. So it's the gravitational path integral integrating over metrics, e to the I times the metric. And then we take a limit to the boundary, z going to 0, some rescaling. I'm going to assume these operators O all have dimension delta. You could take different operators, but for simplicity, let me all have the same dimension. So then it's just z to the n delta times an expectation value of, so basically a bulk correlator in the metric G. Okay, so this expression, okay, so let me just explain. Okay, so where, as I said, these operators have dimension delta. This notation means doing the path integral over the matter field in a fixed metric G. So this is a bulk path integral over phi in a fixed metric G. And this is, these x, z are Pfefferman-Graham coordinates in this asymptotic region. These xi, z are Pfefferman-Graham coordinates for G. Okay, if you're going to do some average like this, you need to know where you're putting your bulk operators. And so this gives an unambiguous location for the bulk operators for each metric.
Are you already committing these O's to be space-like separated?
At the moment, I'm leaving it unspecified. This is supposed to be the general description of what's called the extrapolate dictionary.
But isn't that then a time order?
I'm going to get to that in a minute. This is, yes, that's a key point. And I deliberately did not put the time ordering in yet, but that is going to be a key point. Let's hold on one second. Okay, so this is usually called something like, this is called the extrapolate dictionary. Because you're doing some bulk calculation and extrapolating to the boundary and then getting some boundary correlator. I should point out that in a full non-perturbative formulation of quantum gravity, there is another choice. You could decide to do this limiting procedure after doing the integral over metrics. I prefer putting it in here because it's easier to think about, but it's at least logically possible that you want to set up the correspondence so that you do that after doing the integral over all metrics. Okay, well, let me now, with all of those preliminaries, tell you our resolution of this causality puzzle. Okay, so we want to consider calculating the commutator using path integrals. Now in path integrals, the standard path integral, as Yoshinori just said, always computes a time-ordered correlator. Time-ordered. So to compute an out of, okay, so this is the usual story. You have a space-time, you have some points P and Q, time-like separated, and the path integral over these over operators at these points always gives you a time-ordered correlator. Phi of, in this case, it would be, well, time order doesn't matter. Sorry. Let's get rid of that. Okay. So to compute a commutator, of course, you need to consider the out of time ordered product of fields. And how do you represent that in a path integral? To do that, you need to consider something called a time fold. So for out of time ordered, ordered products, a time fold is a space-time which looks like this. Try to draw this. Let's see. It's a zigzag space-time where you evolve forward up to your later operator, we'll put Q there, then evolve backward to your operator at the earlier time at P, and then you evolve forward again. These kind of zigzag spacetimes are known as time folds. In holography, we have to think about this both on the boundary and in the bulk. So there are both boundary and bulk time folds. If we want to consider something like a commutator on the boundary, we need the boundary to have a certain time fold, and we need the bulk to be asymptotic to a boundary metric with that same time fold. So a more accurate statement of the correspondence in holography So in holography, the first statement of holography should really be that if F is a boundary time fold, required to get the time ordering of the operators of interest, then we should consider a bulk partition function which asymptotically approaches the same time fold with boundary conditions on that time fold. That must be equal to the boundary partition function evaluated on that same time fold. Okay, now for a unitary theory, evolving forward and back in this way without putting any operators is just the identity. So given, some number of operators on the boundary on an ordinary field theory, I could consider a time fold like this, or I could consider a time fold which has many other forward and back evolutions with no operators inserted, and that wouldn't change the answer. However, in the bulk, we're considering full quantum gravity, and I don't want to assume that full quantum gravity is unitary, right? That's one of the big puzzles about quantum gravity and black hole evaporation. Is it always unitary? Might you get different answers or something which is not the same as ordinary unitary evolution? So my goal is to understand a basic property of the field theory, this causality, in terms of the bulk path integral, but I don't want to make extra assumptions about quantum gravity, such as that it's always unitary. So I need to fix this ambiguity in how I choose my time fold. I don't want to allow the time fold to have all these extraneous, forward and back evolutions, which might or might not give different answers in terms of the bulk partition function. So
Barry?
to fix, yes?
Can I ask how you would define unitarity in the bulk independently of the unitarity of the CFT? In other words, what would be a bulk definition according to which you could tell if the bulk was unitary or not?
Well, we don't need holography. I mean, there may not be any dual theory at all, but we could still consider states in an asymptotically anti-de Sitter spacetime evolve with some asymptotic time. And, you know, the statement is that, yes, you would use the asymptotic time, but I would not require that there be a local quantum field theory which is completely equivalent to the boundary. I mean, we wouldn't need all the machinery of holography, right, to ask the question about whether quantum gravity is unitary.
Or is not
I
you're
think
saying that sorry, your statement is that you don't care those things for your purpose, right? To make your point, you don't even need to talk about it because you don't want to assume anything about it.
Right, I'm not going to use it. I don't want to assume anything about it, so I don't really need it.
Well, but the fact that there is a dual boundary theory informs the question that you're asking in the first place, right? We wouldn't be worried about how causality could be violated in the boundary theory by this bulk path integral if we didn't already know we had a boundary theory. I'm just not convinced that there's a good way of defining what we would mean by unitarity in the bulk. I mean, let's say an asymptotically flat space-time. I guess what we mean by it is the existence of some unitary S matrix, right? I think the closest analog of that is perhaps the existence of these correlation functions in the extrapolate dictionary, right? Or I'm asking, what would be the analog of that would let you say in just a bulk way what you would mean by the bulk being unitary?
Okay. I first of all want to say I want to be very careful not to assume too much from holography, because if we assume holography, there's no problem, right? The bulk has to equal the boundary theory is unitary, so the bulk calculation must be unitary. I'm sorry, I'm saying it the wrong way. The bulk is equal to the boundary theory must be causal, the commutator must vanish, and therefore the bulk calculation has to give vanishing commutator. So if we assume holography, there's no issue. And if we assume holography, there's no issue with unitarity either, because the boundary theory is unitary, the bulk theory has to be unitary. What I'm trying to see is from a purely bulk standpoint, assuming that it's given by some path integral over metrics, how can I see that we're not going to violate causality? And I'd like a bulk argument for that, which doesn't assume anything more than necessary. So I don't want to assume bulk unitarity. Now, what it would mean, I think it's, we have imagined some sort of bulk quantum states, and it would be evolving according to some asymptotic time, and we would want that to be some unitary evolution of the state in some suitable Hilbert space. That's, I think what we would mean by unitarity in quantum gravity. But we certainly don't know that, because otherwise we wouldn't be spending 40 years arguing about whether black hole evaporation is a unitary process in the bulk.
Well, in that case, what we're arguing about, right, is whether the information comes out to distant regions. I guess I'm trying to understand whether you're being open-minded about unitarity in that sense, or whether there's some other notion of unitarity that involves Cauchy slices, for example, in the bulk, where you're required to look deep into the bulk to verify whether unitarity holds or not.
I can believe that the appropriate notion of time evolution is boundary time. And if we had some suitable Hilbert space of quantum gravity states and some suitable states, it could be labeled by boundary time, and we could consider evolution according to that.
I see. But so you're saying you simply want to no more assume unitarity in that sense than you wanted to assume causality in that sense, basically. I mean, that's you don't want to sort of that causality come in through the back door.
Sorry, I've lost my screen here. Okay. Yeah, I don't want to assume. Yeah, I didn't want to assume anything more than necessary. And so it would be great to have a proof of unitary evolution in quantum gravity. And but for now, I mean, that after all is another consequence of holography, and it would be another way of verifying a property of holography directly from looking at the bulk. So that would be in the spirit of what we're doing. But since we were thinking more about this causality problem, we didn't want to make extra assumptions about unitarity.
Thank you.
Okay, so there is this issue about which time fold to pick. And so we are going to propose, and this is just a prescription, and I'll show you what works, but there might be other prescriptions. We're going to adopt what we call a minimal time fold. And that means you put in one of these creases only when necessary to describe out of time ordered operators that are causally related and appear in the correlator out of their normal time ordering. So we're simply going to say we want in the definition of holography F to be a minimal time fold and not one which has extraneous forward and back evolution without any operators inserted. It seems the simplest possibility, and what I want to show you now is that it works to avoid any causality problem. So, claim is that this removes the causality puzzle that I mentioned at the beginning. And let me show you why that's true in each of the two approaches to relate boundary and bulk quantities. So for the first approach, this differentiate dictionary, we have 2 points on the boundary which are space-like separated. So the minimal time fold is no time fold. You don't need any creases at all. So for X and Y space-like separated, the minimal time fold is no time fold. It's the same as the original space-time.
Okay.
So that means.
Oh, sorry. Oh yeah, just to make sure that means that you're choosing special Lorentz frame or something, right?
I don't need to. No, I don't need to pick any particular slicing. I mean, it's just saying that the space-time, I have my space-time, I have points X and Y. And sure, I could choose a slice which goes through them both simultaneously.
Yeah.
Yeah, so you can do that if you want.
You need to, right? Otherwise, you need to fall back.
Yes.
Yeah. That's what I meant. Yeah.
Yes. Okay. Okay. Good. Yeah. So let's choose. Okay. Yes. Let's choose a slice in which they appear simultaneously. That we're certainly free to do. And then there is no there's no creases.
Yeah. But you need to, right? That's something I want to know, like a prescription. Of course, it's just prescription. It doesn't mean a physics violating Lorentz invariance, but your prescription requires to go to that frame, right?
Yes, but by minimal time fold, I mean, okay, in your language, yes, minimal timefold means choose your slices in such a way as to minimize the need for any. So if there exists slicing for which there's no creases, use that one.
Yeah. Okay.
But Gary, I guess I was curious then, if you do have a time fold, do you also sort of choose the slices to sort of dip down to the points where your operators are to sort of minimize evolution elsewhere so that there's sort of almost null? Do you choose some kind of preferred slicing?
It's not going to matter for this argument what I do elsewhere, whether it's almost null or not.
Well, then I guess you don't need to answer my question.
I guess I don't need. Okay, let me just finish the argument for this way, and then we can think about other applications. Okay, so if there are no creases, then from the bulk standpoint, to compute a commutator from the bulk, you simply have your usual partition function, which is a function of the sources on this trivial spacetime. There's no folding needed, and the calculation of the commutator just reduces to taking two derivatives of this, one with respect to x at the source phi naught at x, and then the derivative with respect to phi naught at y, and then we have to subtract the derivatives and the opposite order of z bulk. But these are just like partial derivatives, and partial derivatives commute. I mean, you're clearly going to get the same answer taking the two derivatives in this order or two derivatives in that order. And so this differentiate dictionary gives you 0. Just to show you why you don't get 0 if they're actually time-like separated on the boundary. We want, of course, to get non-zero commutators in that case. So if x and y were time-like separated, well, then you would have this non-trivial time fold, and you'd have, let me just draw it in one dimension here. You would have on the boundary the point, say, x and y, and you would be subtracting. This would be y, and that would be x. So you now have sources everywhere along this bigger space-time. You would be taking in one term the derivative with respect to the source here and the source there, and subtracting what you get by taking derivatives with respect to the source here and there. And since these points are different, the answers can be different, and you can get non-zero commutators for that reason. But with a trivial time fold, there's only, the source at x appears once, not twice in this space-time, and so the commutator is always 0.
Maybe this may not be an appropriate question because that's outside your prescription. That's totally well defined, I think. But let me just ask anyway. If you could probably do this like last part of this slide, even in space-like separated points x and y, right? Because you can choose some time slice in which x and y are not on the same time. You can just do that, and then still it has to vanish, right? So in that kind of basis, understanding of this is not this understanding of vanishing of commutator, is still cancellation or something?
You mean if you choose a different, x and y are space-like, but you choose a different slicing, so there is a time fold?
Yeah.
Yeah, then I agree. It's not, right, it still has to vanish.
Yeah.
But
so then it probably, this
it's not so obvious.
thing doesn't kind of work. So this particular argument doesn't work. so it's not almost saying that you have a cancellation where you originally started unlikely, saying unlikely, but
No, I don't think, is this the same as that?
I don't know. But at least this argument doesn't work, right? Because just a different operator, xy and yx prime.
Right. No, I see what you mean. It certainly, this argument doesn't give, it's not immediately zero.
Yeah.
It would have to be zero for a more
Yeah.
subtle reason.
Yeah.
And I think in that case, yeah, you could probably relate it to this unitary evolution. It's probably related to this unitary evolution and the fact that this fold was not really needed.
Yeah, of course, your perception is the simplest way to see it. That's true. And then you can understand why that's the case. But depending on if you do the stupid thing, then it may look like a cancellation. Or that's what I'm saying.
Yeah, I don't think this is quite as, I mean, there's no causality violation issue.
Yeah, you already proved it. Yeah, that's fine. But
right. So I don't think it's quite the same as the original puzzle in terms of the cancellation I suggested at the beginning seems a lot worse than this one.
Okay. Okay. Yeah. Okay. Yeah.
Okay. Well, I'm just about out of time. Let me finish up here. So that's what happens in the differentiate dictionary when you're simply equating partition functions invariant with respect to the boundary conditions and the bulk. But the extrapolate was the case where we seem to have a bigger problem. The extrapolate dictionary said compute the commutator in the bulk and then take the limit of the points. And if the points are time-like related in the bulk, you would think that commutator would be non-zero, and so we should get a problem. But we now, with this minimal time fold, the boundary condition on the bulk metrics has to be the same as it was in the differentiate case. So we still require bulk metrics must have the minimal time fold as the conformal boundary. And when X and Y is space-like, that, as I've said, is no time fold. So it's just, again, the standard space-time with, so this is the conformal boundary with points X and Y over here. So now if you imagine doing a bulk calculation, we want to consider our 2 points, if P and Q in the bulk are in the asymptotic region, they're time-like separated according to the bulk metric. A bulk calculation of that commutator, if it gives a non-zero answer, requires a bulk time fold because we have to allow the later point to appear first and then evolve back to the earlier point. So this a bulk calculation of this commutator being non-zero requires a asymptotic bulk time fold. It requires a time fold in the bulk, which is not going to agree with the boundary condition we had specified. So this violates our boundary condition. And that's the key point. If we insist that our bulk metrics all approach this minimal time fold or trivial time fold on the boundary, we're not allowed to introduce metrics that would allow a non-zero commutator. All the metrics, so with our boundary condition, the boundary condition we've specified, the calculation of this correlator 5p 5q is always time ordered. Always. So it's regardless of the order of the operators, you get the time ordered product. And of course, then they're equal regardless of how they appear in the correlator. And so the commutator is 0. Or the, if you want the expectation value of that. It's 0 because it's always time ordered.
Can I ask a question? It's not, let's focus on just on calculating this particular 2-point correlator. Okay, maybe depending on other correlator and so on, but let's just consider the calculating this correlator. In order for the purpose of calculating these correlators with the phi to be space-like separated, and that means minimal fold means that it's on equal time. And that means that the metric you gave as an example should not be included in this calculation, right? So just simply, for particular purpose of this 2-point correlator, it's essentially you're saying that the previous metric in which you can go to less than pi should not be included, right? Because
No. Metrics that violate boundary causality can certainly be included here. What I don't allow is any time fold. So in any of those original metrics, so we can allow all of those metrics that violated boundary causality, but in those metrics, calculations of expressions like this are always time ordered. If these operators are in the asymptotic region, this always has implicitly a time ordering symbol in front. And so this always ends up being the same. The two terms automatically cancel. The metric can do whatever it wants. It's just a nice metric as far as the bulk is concerned. It approaches some boundary metric, and we just never introduce the time fold that you need to calculate the out of time ordered product.
Thank you.
Okay, I'm out of time, and that was pretty much the last thing I wanted to say. So this sort of resolves the puzzle. Let me end there and take any further questions. Thank you.
Thank you, Gary.
Thank you.
Questions?
Well, still, can I ask you this? If it's a time space like separated, and you said that this metric violating, a boundary causality, like a smooth bulk metric which violates a boundary causality, can be included, but it has to be included in a way that it's trivial time fold. So the probably phi p phi q and then phi q phi p term, the contribution from those metrics are canceled. Is it always equivalent not to include that kind of metric? Can you show that? I mean,
No, because suppose I don't calculate the commutator. Suppose I just want to calculate a 2-point function. Yeah, so if you want to just calculate phi p phi q and not a commutator.
Okay.
So
still include.
Right. So these metrics will certainly contribute to it.
Okay.
In fact, one interesting question which we don't answer is, what effect do these boundary causality violating metrics have on correlators in general? So if we don't worry about the commutator, which we now say will be 0, these metrics which violate boundary causality certainly should contribute something. We certainly don't know that they always are integrate to 0.
But is it really
we have
measurable?
any example? Is there any example where it's known that they contribute a non-zero amount?
No, because that would require that we could do the full, quantum gravity path integral and see what the answer is. You can't do this in low dimensions, right? In very low dimensions, JT gravity Well, the equation, you integrate out phi, and then you find that the scalar curvature is -2, so the metric doesn't fluctuate. In two-dimensional JT gravity, the metric is rigidly ADS2, and you don't get any fluctuations of the light cone.
My question is that if you really focus on, because it's suggestive that the commutator, the contribution from those metrics disappears, and commutator is observable. But coordinator itself is not, right? Really, you have to go to, say, like a pole and residue and extract, amplitude and stuff. So is that still possible that effectively, it doesn't look like that way, but so for example, think about some time-like separated two-point commutator, phi p and phi q, and time-like separated, but it's still you compute the commutator. And then minimal time fold is different in different term, right?
Right.
And then should you still insist that these metric must be included in each term?
Well, let's see, are you talking about in the field theory? In the field theory, you would include this, if you had just a two-point function, two time-like separated points, and you have some two-point function, you would choose the particular time fold to represent the ordering of operators.
Yes.
So
yes.
if you choose it to be time ordered, you get no folds. If you choose it to be out of time ordered, you have to have the time fold. So it's dictated by the order of operators in the correlator.
Yeah. And then the question is that you include these metrics contribution when you do the partition.
I don't see any reason not to include them.
Okay. And then you're probably guessing or claiming that they don't cancel in that case. Namely, it leaves a physical effect on the commutator, because I don't want to. I want to go to commutator. Commutator is right, observable.
Yeah. They shouldn't cancel if the points are time-like separated on the boundary. They should not cancel. The boundary commutator is not zero. The bulk calculation has to be non-zero.
Mm-hmm.
So yes, so you would get a non-trivial time fold on the boundary. We would then allow the bulk metric to have a non-trivial time fold. It would be required, and we would be able to get a non-zero answer in that case.
Okay, so that makes it clear that you're not suggesting, even physically, that you're not including this metric. It's very different proposal. Yeah,
I don't see any argument to throw these metrics out. As I said, there's lots of them, and there's nothing wrong with them as far as the bulk, physics. They look like perfectly good metrics if you don't worry about the boundary and causality on the boundary or anything.
Okay, thank you. Yeah. I just think that in the end, maybe same thing and so on, but it looks different.
Yeah, I mean, the key thing is that they don't satisfy the null energy condition, right?
Yeah.
That was the property of the class, but that's a solution. I mean, these are off-shell metrics, so
yeah,
we shouldn't be requiring that.
Okay, thank you.
So Jerry, can I understand your minimum time fold restriction as a most convenient way to compute the commutator, or is that setting a new rule to the gravitational path integral?
Well, the minimal time fold was a way for us to remove the ambiguity in what boundary condition to pick, because the field theory, allowed for all sorts of arbitrary, evolution forward and back, which didn't change it. We didn't want that ambiguity in the bulk. So we fixed that. It seems like the simplest procedure, which allows you to compute out of time ordered correlators. I don't know what.
Yeah, so at the boundary, so you could choose weird kind of time folding, and
right. In the boundary, there are many kinds of time folds you could choose, which don't do anything because you just get the identity.
So even in the bulk, you could get some weird kind of time fold, but in the end, they should be give the vanishing commutator. That you expect.
That's what I kind of said.
Right.
You
Yes.
could do in this weird time fold, even if P and Q are separated in principle.
Right.
And
right.
then it probably would seem like weird cancellation. But what Gary was saying is that depending on correlator, there is a good gauge or good Lorentz frame in which you can go to. And then that frame depends on the particular correlator. If a PQ is a different point, you can go to different time slice in which P and Q are on the same time slice in such a way that it can be viewed not as a weird cancellation, but it's simply understood. There is a basis that, but if you do a stupid thing, then probably something weird is probably happening, right? But there is a reason, because you can have a basis or Lorentz frame in which things doesn't look like weird cancellation, but it's just simply a partial derivative commute and so on. So in that basis or in that frame, things looks easy. It's like just choosing particular useful gauge or frame or time slice. It's just, is that true? Like that's good kind of, am I getting things right?
Yeah, I agree. I'm still not happy with this. You say weird cancellation, and you're referring back to my early, description of the puzzle. The causality puzzle is requiring this strange cancellation. I don't think they're the same. I don't think they're even similar. I think that there's an issue in the integral over metrics that these causality violating metrics have to vanish, which is not part of the story about how you get zero commutator when you just put in these trivial time folds that aren't required.
So then you're saying that you expect that even if you do this time fold way in space like separated, then the contribution from this boundary causality violating smooth metric is canceled trivially, not like e to the IS or something, but it's if it's space like separated, it cancels trivially, and then if it's time like separated, it doesn't cancel. Is that what you're feeling?
Well, it's true that it should cancel when it's space-like and not cancel when it's time-like. That's true. Let's see. But you can ask your question just in the boundary theory, right? I mean, you could say, if you just have an ordinary quantum field theory and you have space-like separated points, but you choose a frame where one is after the other and you put in a time fold, why is it zero? That I think will have an explanation which doesn't require, I mean, you're not changing the metric there. I mean, right, the metric is fixed and all you're doing is, copying part of it or evolving backward in the same space-time. So the metric is not dynamical in any sense. There's no issue of causality. It's just an issue of evolution. And I think the answer there will end up being, well, something about the path integral representing unitary evolution and get an explanation which doesn't require any sort of exotic cancellations in the path integral.
Then probably this minimal folding requirement may not be needed to, I mean, it's just, you can also do this in the space like separate case. And if you're just carefully looking at things.
If we knew, if there was an independent argument for unitary evolution in quantum gravity, then we probably could get rid of this minimal time fold.
You don't want to do that.
Yeah, it's
yeah. Okay. Thank you.
Any more questions?
But if the causality violating metrics end up contributing to some, end up contributing to when they're allowed to contribute, is it fair to say that the precise way that you define what the minimal time fold looks like is going to matter for that? I mean, what I'm worried about is, again, if we just try to for example, whether we try to use some particular simple foliation near the boundary, or whether we just try to deform the slices in such a way that they pick up only the operators and sort of try to move up and down in time as little as possible away from the light cones of these operators.
I don't, well, okay, let's see. If you're talking about just the 2-point function, and you're talking about one of these boundary violating metrics, well, if the 2-point function is time ordered with respect to the bulk time, there is no need for a time fold, right? The time fold would only be needed if you wanted to consider the out of time ordered correlator.
Right. But then I could ask whether I should just deform the slice only sort of locally to pick up the operators and, up and down in time while keeping it fixed far away from the operators, or do I need to?
But you're
maybe
still
that's the wrong picture there.
You're imagining the boundary points, the points on the boundary, these points are still space-like separated, or do you want the boundary points to be time-like separated?
Time-like.
The boundary points are time-like separated.
Yeah.
Okay, and it's a out of time ordered correlator. So we definitely have a time fold at infinity on the boundary. And the question you're asking is how we bring that inside.
Yeah.
Yeah, I think that's, it shouldn't matter. It shouldn't matter. There should be, well, maybe I should.
Intuitively, I'd be very surprised, right? If it's important because you don't know whether the bulk is unitary and so on. If it's important not to introduce sort of unnecessary time folds, which I understand your prescription to be, then it would seem unnatural if I was allowed to introduce them when I have, if I was allowed to introduce them very far from the two operators whose out of time ordered correlation function you're trying to produce, because in some sense it just, if it caused any trouble, if there were no operators at all, then it should still cause trouble in that case.
Well, let me mention something which I didn't have time to go into in my talk. And that is that we expect the bulk gravitational path integral to include time folds, bulk time folds that are trivial at infinity. I mean, even with no time fold on the boundary, because this is just related to integrating over positive and negative values of the lapse. And Jim Hartle showed long ago that if you want to impose the gravitational constraints, if you want your wave function computed with a path integral to satisfy the Wheeler-DeWitt equation and not have delta functions on the right-hand side to be more like a propagator, if it's actually going to solve the constraints, you need to integrate over positive and negative lapse functions. And so that's like having time folds in the bulk, which are trivial at infinity. So that is sort of part of the bulk path integral anyway. But that shouldn't, well.
So the thing that you're forbidding, right, then are time folds sort of in the bulk slices near the boundary.
Right. It's time folds which actually extend out to a non-trivial time fold at the boundary. It's something which changes the conformal metric on the boundary.
I guess what I'm asking is if you have two time-like separated points on the boundary that force you to introduce a time fold, though,
right?
Then I would somehow find it surprising if that time fold was allowed to extend out to infinite distance in that on the boundary directions, since you were forbidding the same thing in those cases where the time fold wasn't necessary anywhere. Just by sort of cluster decomposition or whatever. I mean, it should be, if it caused problems when you didn't need any time fold, then it should still cause problems far away from where you needed the time fold, I guess is what I'm trying to say.
I see. So you mean on the boundary, you have two time-like separated points, you draw surfaces, the time fold, but far, far away from those points on the boundary, you require that those surfaces agree maybe or something, or I don't know. You want to say that?
I mean, I would have thought that a very natural there's probably a natural way of sort of defining a minimal time fold in terms of,
So
you
it
know,
sounds like we're back
light
to
cones.
yeah. Causal
Yeah, light cones
diamond.
of these operators. Yeah, exactly.
I see.
Exactly. Just do them in the minimal region that you can do them in.
Huh. Well, that is an interesting question, which I have to say we've not thought about what happens when time folds are sort of limited to sort of just some causal diamond region or something close to it.
I thought
Yeah,
that
I mean, I guess it depends on how worried you really are about the unnecessary time folds causing trouble. But I think if they do cause trouble, then they're still going to cause trouble far away from the operators that force you to introduce a time fold.
I see. Well, thank you. That's something we should think a little bit more about. Yeah.
I think you're saying in a time-like separated case, you cannot go to that time slice that all the operators on or two operators on the same slice.
No, you certainly can't. But Raphael is saying, let's go far away in a space-like direction from the operators of interest.
Yeah.
What are the surfaces doing? What is a crease doing way out there?
Yeah, but you want to do as much as much as you want to agree with these two surfaces. So you can do other than this near time-like region. Of course, you want to do as much as you can to, you know, zero fold. I mean,
Yeah,
I
so
think that's what I'm
Raphael's
saying.
yeah. If it's a time slice is not time slice can be completely arbitrary, then you can, but may not be, because you may have only like inertial frame type concept, because only conformal symmetry and a high dimension and the conformal symmetry is allowed. We are not doing general relativity. We're doing rigid theory on the boundary. So in that sense, it may have to be in an inertial frame. You may not be able to do whatever the arbitrary, I mean, you have to be inertial frame. It's Lorentz
Nobody forces you to, even in Minkowski space, nobody forces you to use an inertial frame to do time evolution. Right. You can use any slices you like.
No, I think it's clear that from the boundary perspective, it will be totally irrelevant what how you choose these surfaces far away from the operators, right? I mean, the ordinary field theory, this shouldn't matter at all, but the connection is to holography and what we assume about the boundary condition for the gravitational path integral. Yeah.
Yeah, I still don't understand if these 2 points are space-like separated, and yet you do this time fold, and how you see that, that cancellation. I already understood that you can go to this slice.
I think the prescription that I'm suggesting would exclude doing that. It would forbid you from doing that. You wouldn't be allowed to do a time fold in that case. Yeah. And it's a covariant statement. It has nothing to do with what slice you choose.
But you can.
Yeah,
you can't do it anymore. If the prescription is that you have to do the time fold only in the causal diamond spanned by the points that.
Oh, is that what you're saying?
Yeah, well, that's what Raphael is saying.
Then it means that you can't do path integral calculation in a boundary theory. Because I thought that the message.
No, in the boundary theory you can do in the boundary theory you can do whatever you like. Like the question is what time folds you allow in the bulk when you do the bulk calculation.
But I thought that the key point was that in the bulk statement is a path integral. In a boundary theory, you shouldn't. Oh, you better not to make a statement in operator language. You have to go to path integral language because you're comparing path integral with a path integral. Then you have to have a folding. Therefore, the asymptotic boundary condition must also respect that folding. I thought it was just that.
Yeah, it is
and
that.
You say more than that.
No, Raphael is saying, what do we mean by the fold far away from the operators and how exactly the fold takes place? And I was drawing these straight lines and everything, but Raphael, I think, is pointing out that it's not a precise notion of a minimal. What I said was not a precise definition of a minimal time fold. I was not specifying how we draw the surfaces sort of at large space-like separations.
But he's saying that a certain
just
time fold,
a causal diamond.
I think you were saying a certain time fold, it's allowed from the boundary point of view. You can't allow that as an asymptotic boundary condition of the bulk, right? That's what you're saying. It's prohibited to have this time fold far away.
But I thought that's already true in the version that Gary presented. There are time folds. You can always introduce arbitrary amounts of time folds on the boundary and it won't cause any trouble. He's already forbidding some of them.
Right.
No, in his prescription.
in the bulk.
But in
Yeah.
his prescription. But I'm saying
And I'm
that
just saying,
probably
I'm
you
trying
can
to make
do
that a little more
anything.
strict, that's all.
Okay, so this is different. I mean, then if you do arbitrary thing in the boundary, just simply the physics looks more complicated, or you can't do that. That's a different statement. And you're suggesting it may be that you can't take other than minimal type time fold as a asymptotic boundary condition of the path integral in the bulk. I think that the other possibilities, you can do whatever you want, but the physics looks simple. Like you don't need to see some miraculous cancellation if you choose right time fold. In the wrong time fold, it just simply goes to 0, but it's very miraculously looking.
So that could be true independently of whatever refinement I was imagining to Gary's suggestion, right?
No. You're saying that other than the minimal time fold, specific time fold, you can't take that as an asymptotic boundary condition of the bulk path integral. What I'm saying that the possibility is that you can do whatever, but the things look simple only if you take Gary's prescription. But you can't do that. And you're saying that you cannot.
Well, again, I don't understand how they can look simple.
Because you can put.
Let me just finish. I don't see how they can look simple. It's this cluster decomposition argument. I don't see how they can only look when you're not forced to introduce a time fold at all in the bulk. Then we would say they only look simple in that case. But then if I have some operators and it force me to introduce a time fold and I want it to be on some nice, whatever, inertial slice, then I'm forced to do at very large distances precisely the thing that was causing it to not look simple in your language in the case where I needed no time fold at all. I don't understand how that is consistent. So whatever applies in one case should apply in the other. That's all
it's just saying that if the two operator, this time fold, I think if he's taking correlator dependent. Suppose you want to compute some correlator, a 2-point correlator, space X separated, and you could do in this time slice where the 2 points are not at the same time. Then the first term is no folding and second term is a folding. Then he cannot use his particular argument, but it still must be 0 and just simply looks complicated, some complicated cancellation. But you can do the time evolution in a way that the 2 point is on equal slice. And then it's obvious because it's just a partial derivative, it's just a commuting and so on. It's completely obvious. But I'm saying that you must be able to do not like that minimal thing, but it's some stupid way. And then use that stupid time folding as an asymptotic boundary condition of the bulk path integral. And I think you still see the final result being 0. Okay.
So I think we've turned this into an internal Berkeley discussion. Gary, you are allowed to voice an opinion if you like. But if not, then I think we should probably draw it to a close and thank Gary again. And I guess we'll have an opportunity to talk more. Gary, are you able to join us for our meeting with the speaker? It's usually the following day.
I suppose so. You said 1:30 tomorrow, is that right?
Yes.
That would be fantastic.
And what is the Zoom link for that? Is that?
I will send.
You'll send it to me?
You will get it, yes.
Okay.
Maybe I may want to get it too then.
Yeah, I'll remind you. No problem. It's the same as last time though. So yeah. All right. So thanks so much, Gary. That was a really inspiring talk, as you can see.
Okay.
And we'll see you tomorrow.
Great. See you tomorrow.
Let's thank Gary again.
Bye-bye.